So, we have discussed about the orbital quenching of paramagnetic salt. So, in case of iron salt, iron group salt, so this orbital quenching is found, whereas in case of rare earth salt, so in that case there is no orbital quenching. So, why it happens that we have discussed. So, this paramagnetism whatever we have discussed, that is for ion solid or ionic solid, that is basically insulator, material. Today I will discuss about the paramagnetism for metal. So, this paramagnetism in metal. So, we are familiar with metal, and as we have seen that metal have the free electrons, and using the quantum theory we can see that these electrons are arranged in dependent energy levels, and near the Fermi level, Fermi energy, those electrons participate in conduction. Okay. So, in this case also, when we discuss about the paramagnetism in metal, so this is similar behavior will be considered, means electrons near the Fermi level will contribute in paramagnetism. Okay. So, experimentally it is found that this paramagnetism in metal, this chi susceptibility, it is independent of temperature. And experimental result is nicely agree with this mu 0 n mu square divided by 3 kV, 3 kV. So, in case of paramagnetism, we have seen, in case of paramagnetism of insulator material, that we have seen this chi is like this, it depends on temperature. Okay. But in case of metal, this is not the case. So, it has to be independent of temperature. So, this temperature dependent will not be there. So, that is what we want to see here, how it is independent of temperature. So, this expression for paramagnetism in ionic salt, like iron group salt or this rare earth salt. So, here paramagnetism in metal, that is basically called Pauli paramagnetism. Pauli paramagnetism of metal Pauli paramagnetism of metal. So basically mainly for conduction electron, this paramagnetism mainly for conduction electron. So this so if we take a metal, so it has free electrons. Now its electrons are, we can consider that the electrons are arranged in energy level So this type of diagram frequently we will see in book. So this is basically energy E, and this axis is density of states. Okay. So density of states, you know, this number of states per unit energy. So that is basically number of electrons per unit energy, if in each state these electrons are there. So here free electrons, if we consider the spin of the electron, so in normal metal half of the spin is up and half of the spin is down. So we can show that if this is the Fermi energy, so this level so this half, if we take this half is filled up by up spin and this half is filled up by down spin. So these are density of states. So at lower energy, density of states are less, okay, because this is the density of states. So now if you go at higher energy, density of states will increase, okay, because it is increasing, right, So density of states increases, okay. So these are the basically energy levels. So here this density of states increases. So that way I have not drawn this diagram, just it will increase compared to the lower energy, okay. So half of the electrons are spin up and half of the electrons are spin down. Now if we do not apply any magnetic field, H equal to 0. Now if you apply magnetic field, so what will happen? So spin up electron, say its magnetic moment, say it's mu v, and this energy due to magnetic field, energy will be mu v dot h, and then it is minus, right. So this is the energy due to applying magnetic field. So this energy is for spin up electron, spin up electron, right. This is the energy for spin up electron. Similarly, for spin down electron, the energy will be mu v minus h dot h, okay. So here it is plus sign, because mu v, if in this case is plus up and this other case it will be down, okay. So So, so in the case of applying magnetic field, so what will happen? This spin of energy of the spin of electron will change, right, for each electron by this. Okay. It is independent of energy level. So, it will be shifted by this amount, and this it will be shifted by downward shifted by this amount. So, this if I draw for applying magnetic field. So, what I will see? I will see the if this the initial level. So, what we will see? So, from this spin up one, it will be shifted by minus mu v, it will be shifted by minus mu v, okay, whereas this one will be shifted by plus mu v, okay. So, but at equilibrium, so Fermi level, here this basically EF Fermi energy, this is the Fermi energy. Okay. So, now here you can see this is the spin up electron and this is the spin down electron. Right. So, this is for applying, after applying magnetic field, H is not equal to 0, So, so while we are using B, so let us write B, magnetic induction. Let us write B. Okay. So, this is the energy separation, it's 2 mu v B, right. So, now here if I just take them in this condition, so equivalent diagram I can draw like this, as if see it has to be symmetric. So, as if I just want to find out the net spin up electron, here we can see these spin up electrons are more, because energy are lower energy states are more. So, here, so this is the spin down. So, net spin of electron, it will be like this, we can represent by like this. Okay. Okay. So, this minus from this one, okay, then that will be the net spin up electron near the Fermi energy, Okay. So, this is the axis of density of states, this is the axis of energy. So, that you should write. So, this okay. So, now under by application of magnetic field, I have the imbalance between the spin up and spin down electrons. In this case, this it was balanced, it was 0, net spin up or spin down was electrons was 0, but here we have net spin of electrons are there. So, if n is the number of electrons per unit volume, n is the number of electrons per unit volume, and n plus is the number of spin up electrons, and n minus is the number of spin down electron. So, per unit volume. So, this minus this will give me net spin up electron. Now, each electron will have the magnetic moment mu v, right. So, this will be the magnetization, because this is the net number of spin of electrons per unit volume. So, this is the magnetization. Okay. So, spin off. Now, you see density of states, if you remember, density of states is proportional to square root of energy. That is why it is parabolic. Right, because of this. Okay. So, number of spin up electrons will be or density of spin up electrons, it's will be d at energy E. I think this the energy for it will be here it's I think mu v b. Okay. So, total number we will get if I integrate total number of states, integrate minus mu v b to Fermi energy. So, this will give me in plus. Okay. So, this I can break it. So, basically I can write 0 to Fermi energy, so that is okay. It has to be dE, okay, and then plus minus mu v b to 0 minus mu v b to 0. Okay. For this will be so this for this case each electron will have the mu v b energy, and for this I can write what will be the things is total number of electrons is half, right. Total number of electrons is half, means half coming from this for this one things I should tell you that total number of electrons n. So, here we have considered for spin up and spin down. So, we have separated, so that degeneracy we have taken care. Okay. That is in total number of n. So, n number that spin up and spin down both are there, right. For each one state is assigned. Okay. So, in density of states, so that degeneracy is accounted. So, for each level, one for the spin up and one for spin down. So, whatever the total density of states, so half will be for spin up and half will be for spin down. Okay. So, half, and then for each one this energy is mu v b, and this density of states. Okay. So, this for minus mu v to 0, for this you will get. So, here minus sign is there. So, that is why this will get this term for n plus, this is for n plus. Similarly, for n minus, it will be plus mu b b to Fermi energy, So, this d is basically epsilon plus or energy plus, this will be minus mu v b. Okay. Because here energy will start, this energy will start from here. Okay. So, E minus this. So, because its origin as if from here. Okay. So, E minus mu v. So, starting count from here. So, this up to here. So, here it started from here. Okay. So, that is why E. So, 0 is from here. So, this amount is added with this. So, in density of states, that is why it is E plus mu v b. Okay. And then this is d. So, that will be basically n minus. So, that will be n minus, and in this case you will get this in same way, that this one can write 0 to epsilon f, then density of states E d, then minus. So, this is taking 0 to E f means from here to here. So, minus this part, which are having mu v b energy. Okay, mu v b energy. So, here I will get like is here plus, because I have to add this part. So, here minus, because this above this. So, this plus this minus for this part. So, this half of the density of states, and for each one is mu v, energy is mu v b, and then is density of states. So, density of states for each energy, it will give you the number of states, means number of spin down electrons, and half we are writing this because half of the electron is spin down and half of the electron is spin up. Okay. So, now this from here, this n plus minus n minus. So, this will be m. So, I can write m equal to n minus, n plus minus n minus. So, here from here you can see this is the n plus, this is the n plus and this is the n minus. Okay. If you take difference, so this will go. Okay. So, this will go because this gives the same number, okay, initially. Okay. So, with respect to 0 to E f. So, here whatever 0 to E f, here whatever 0 to E f, 0 to E f. So, this part basically it will cancel each other, only this part will remain, this part will remain. So, this is the Fermi energy was basically here. Okay. So, spin down just it is decreased and spin up increased. So, thus the net spin up will be difference, that spin up will be double. Okay. So, basically this the part. So, this part from spin down, spin down for this part and this part for spin up. So, if you take difference, so this plus this, right, and this will cancel each other, this will cancel each other, and this half from the spin up and half from the spin down. So, as a whole this difference is basically this net difference is just double. So, this plus this will be the net spin of electrons. So, this is giving me mu b, b and density of states, okay, and then mu b is there. So, mu b square, that is the n. Okay. Now, this b I can write, this b I can write mu 0 h, mu 0 h, and this E f here I should write because it is near the Fermi level, okay, near the Fermi level. So, this I should write density of states at Fermi level, density of states at Fermi level. Okay. Now, you remember that density of states at Fermi level d E f equal to 3 n by I think 3 n by 2 kV, 3 n by 2, 3 n by 2 E f, 3 n by 2 E f, by 2 E f, and you remember E f equal to kV T f, Fermi temperature. So, this equal to 3 n 2 kV T f, that is the Fermi temperature. Okay. Then if I put here, I will get mu 0 mu v square, and then basically let me write chi equal to m by h, So, this is mu 0 mu v square, density of states at Fermi energy. So, it has to be f is 3 n 2 kV T f. Okay. So, that is giving you chi equal to 3 by 2 mu 0 n mu v square divided by kV T f. Okay. So, this is the susceptibility of paramagnetic metal. it is called this Pauli Pauli susceptibility of paramagnetic metal. So, here you can clearly see that this expression, this chi is independent of temperature. It is independent of temperature, independent of temperature, okay. So, as I mentioned earlier that I will show you the expression for paramagnetic susceptibility of metal, which is independent of temperature. So, this is the right time for me to show, and that clearly you can see. Okay. So, this is, in this case, this whatever this diagram I have drawn. So, this very useful diagram, you have to be familiar with this diagram. This is energy, this is density of states. So, what is the meaning of this? Okay. And how I have drawn this one from here to here, right, after applying magnetic field. Okay. So, in case of spin up, energy goes down. In case of spin down, energy goes up. Okay. So, net spin up and spin down, if you just with respect to Fermi level, if you draw corresponding to these diagrams, so it will be just net spin up electron will be this, right, and whatever here we have calculated spin up, spin down, thus one can follow this diagram and can take the limit of integration, and find out. Okay. So, this is the paramagnetic susceptibility of metal of conduction electrons, and which is independent of temperature. But in case of paramagnetic susceptibility of insulator, oxide or rare earth or this iron group oxide. Okay. So, this ionic solid basically, for that case it is, as you have seen, this chi is inversely proportional to the temperature, that is chi equal to C by T, right, that Curie laws. So, that we have seen. So, I have discussed enough about the paramagnetism. So, in next class I will discuss about the ferromagnetism. So, I will stop here. Thank you.